All right, we're about to get started with our lab. Test went well yesterday, so I trust if you're watching, you did well on your test also. Your homework tonight is to get you ready for chapter 12, which we'll be starting in our next lesson. I need you to read over pages 172 to 176. Read pages 172 to 176, and on page 184, I need you to answer questions 1 through 3 and 6 through 9. Page 184, questions 1 through 3 and 6 through 9. What we're going to do here in just a moment, Gavin, is we're going to do some of the labs. I'm going to have to do that non-recorded so the students can be in them and working on stuff. And then once we've got something accomplished, I'll go ahead and record what the results were. And since y'all got to leave early for pizza day, I may do all those little recordings after class if we can rig it that way. So we'll kind of do this lesson in pieces and parts. All right, so what we have here is a class 1 lever, and we've got the meter stick balanced at the 50 centimeter mark, the halfway mark. Now, we did observe before we did the test that this meter stick doesn't balance perfectly. I'm not sure if it's this knife edge that causes it to imbalance or if the mass of the meter stick is not perfectly in balance. But you'll notice he's got about 10 centimeter lever arm here for 500 grams. We've got about 43, 44 centimeter lever arm balancing with 100 grams. So again, we've got 100 balancing with 500. Theoretically, then we would need a 5 times length lever arm. It's not quite 5 times, but it's pretty close. Again, just, there's real life math in here that things aren't perfectly balanced. And again, as I mentioned, we'll figure out how to account for the mass of the meter stick in chapter 13. All right, so here we have what could be an example of either a class 2 or class 3 lever. Now, I had the really long string here. I didn't want to cut it. So obviously you can see there's a little bit of just loose string hanging here. That weight may affect things downward a little bit. A little bit of loose string here. That may be affecting the weight downward a little bit over there. But essentially what we have here, and of course the meter stick is not balanced, right? The meter stick right now, if I just took these weights off completely, it would obviously weigh down that way because there's more mass on that side. Unfortunately, we're not there yet. Chapter 13, we'll talk about how to deal with the mass of the meter stick as well. But essentially what you see here is a very short lever arm from the fulcrum point, which is just a knife edge balance, to 500 grams of mass right here. Very short lever arm. On the other end, we're balancing it with 100 grams. And the 100 grams, of course, is going upward. It's just redirected downward. But we basically have 100 grams worth of force lifting up. And this would be like the wheelbarrow, right? Here would be the wheel of the wheelbarrow. This would be the load. And then this would be lifting up on the other end. Or you could think of it as class 3. And here's your wrist, for instance. Here's where the hands put in force. And they're able to balance out at the other end. And you see that, again, just very small movement here with more force is able to put out a greater distance on the other end. Okay, so class 2 or class 3 lever is what we see here. All right, the last thing I wanted to show here, Gavin, is something I actually did not get to show to my students, and it involves spring scales. Now, what I've got here, if you look closely, is a spring scale that's rated for half a kilogram. Rated for 500 grams. And what you see here is a 500 gram mass. And notice that the spring scale, obviously I'm alleviating some of the weight here. The spring scale goes down depending on the amount of force that's being applied. This one caps out at 500 grams. That's what we've got on here. To verify that as well, we could test it with another spring scale. And this one goes up to 10. But you'll notice if you can read the numbers, it goes just about, when we're looking at the weight, just about to that 5th Newton, that 500 gram mark. Now, that's how much force is needed to lift. Obviously, to slide something is much easier. So let me actually flip this the other way so maybe you have a chance of seeing it here. So as I pull this along at a roughly steady pace, you can see that the spring scale is registering. It takes about a Newton of force to slide it across that felt. About a Newton or so of force. Well, that means that the coefficient of friction would be about 0.2 between this cylinder then and this piece of felt that's on top of the shelf that I stole from Miss Morse's bookcase. Did not want to scratch the shelf, so hence the felt. Well, if I were to incline this a little bit, now obviously if I had this thing in a rolling state, we understand it would just roll down the inclined plane. That's not what we're after. If I put it like this, though, you notice it doesn't slide. Even though there's a weight component that might cause it to slide, there's enough friction here. So I want to notice the difference then when I incline it. And so if you watch here, and again, the goal is to pull this at roughly a constant speed. You'll see we're up to about 1.5 newtons. Took an extra ½ Newton because now not only is there the friction I'm countering, but it's the weight in the X. But again, it would take 5 newtons to just straight lift it to this level. By dragging it up to that level, took only 1.5 newtons. If I then incline it even more, there's going to be more weight in the X. So let's go and get a bigger incline here for this shelf. And I believe now, if I were to just set it here, you'll notice that it slides down on its own accord because there's a weight in the X factor that's significant enough to overcome friction. Well, now when I hook it up to the spring scale, you notice it takes between 2 and 2.5, right about 2.5 newtons of force to pull it up the incline now. Again, there's greater weight in the X, but again, that's 2.5 newtons of force applied, but it was able to lift 5 newtons upward. So with this particular angle, we get an IMA, or an AMA, I guess you would say, of 2, lifting 5 by only applying a force of 2.5. So I want to look at that with you here as well. All right, so what we see here is a wheel and axle. We've got, as you can see, different sizes of wheels. And there's the smallest, middle, larger, and largest. And the diameter of the radius rather, of this second wheel in is half the radius of the larger wheel. So because the radius is half, I can balance half the force. So what I've got here is 200 grams balanced with 100 grams. Because I have 2 more force on the smaller wheel, I need less force on the larger. I'm holding it too high. Because I have more force on the smaller wheel, I need less force on the larger wheel. And the premise again is this, that for instance, in order to lift something that's heavier, as long as I'm turning the larger wheel, it can stay balanced wherever it's placed. And again, this is the example that I used. I keep holding it too high. This is the example I used of the well, right? You're turning the handle. Well, you're turning the big handle wheel as the larger amount of force comes up on the smaller end. Conversely, if you turn the small wheel, you'll multiply speed, right? And so, oops, I turned it a little too far there. But you could see that as turning the smaller wheel multiplies speed there, and there you go. All right, so anyway, hopefully that helped for the wheel and axle. All right. What we see here is just a single fixed pulley. And you can see that, and there's not a lot of movement here because it's a long string I'm going to need here in a minute. But you can see that 500 grams balances 500 grams. All I've done is redirect force with a single fixed pulley. What I had the students do, though, was to kind of weigh in their hand what it feels like to lift up on a 500 gram mass. And then I went ahead and fixed this end here. I'm going to just do it with a knot this time. I'm going to fix this end here and ran the cable through the movable pulley. And attached the movable pulley and said, okay, so you kind of get a feel for what it feels like to lift 500 grams. It's just about a pound. Okay, now lift this. And it just feels a little bit easier. Now notice how much I'm lifting the string, right? So my hand is here. Notice where the weight is. It's right there on the plate. So as I lift, notice how far I had to lift. Notice how little it lifted. I put in twice as much distance. And we can actually see the math on this if we have a, and I didn't actually have, there's one. Okay, if I actually put a 200 gram mass here, now the 200 doesn't quite balance 500, but as soon as I add an extra 50 to it, cause it to be still first. The 250 should balance the 500. It's not quite balancing. It was balancing earlier. I'm not sure how much the angle, I think the angle may have some effect on it as well. So let me pull this in here. There we go. Okay, now we can see how, again, it's hard to quantify upward motion, but by looping it over a pulley that we've already demonstrated shows us this, we can see that, okay, we've got IMA of 2 now. And so 2 strands lifting now. And again, that was the premise even before I showed the math on how 250 is balancing. You take this off. The point is, it's just easier to lift this than to actually just straight lift. Like lifting this way versus lifting this way, because you're lifting twice the distance while you're doing it. There's a contrast on the fixed pulley and the movable pulley. Hey Gavin, wanted to go over one of the block and tackles that we put together. We did not have time to put together an IMA of 6 or 7. I was kind of hoping I could get an IMA of 7 put together. We didn't have time for that. We got as far as an IMA of 4. So what you'll notice in this pulley system is there are 5 strands. 1, 2, 3, 4, 5 strands going across. But obviously the free strand is down. That's just the easiest way to do this. And so with the free strand going down, that gives us an IMA of 4. So what you see here is a balance of 250 grams here, a 200 plus a 50, and here's 1,000 grams. And notice that they balance evenly with each other. So where I put them, they stay. Realistically, I could probably balance, as you see here, 200 grams with 1,000 because there's so much friction right now. This is kind of sticky cable, and so you can really balance 200 with 1,000, but that doesn't mean it's an IMA of 5. It's just because of frictional force. But 250 is the perfect balance here with 1,000 IMA 4. So the point that I wanted to make was obviously then I made 2 points to the class here. One is that for a crane, of course, it's not just straight lifting, it's winching, right? Wrapping the cable around with a motor. But as it wraps and wraps and wraps and wraps and wraps, it's not exerting 1,000 grams, for instance, of force, whatever the force would be on that, to get the object to lift. Rather, the winch only has to exert, for instance, if this were a similar cable setup, has much less force needed because of the pulleys, because of the block and tackle. The other thing I made the allusion to is imagine for a moment that you're working out on workout equipment. Well, you know this, that as you move the object, the plate goes up and down. So picture the little one now as being the plate. That's more the output. Think of your input as the bigger one. If you have enough pulleys and you can make those plates really move through all the cabling, and of course there's going to be some friction that's accounted for in those machines as well, you can get a good workout with a relatively small plate of weight or a few small weight plates. So for instance, when I was in high school, and I was, benching 150 pounds or 100, I think 160 pounds was kind of where I capped out. I'm not a big guy anyway. But when I was benching, 160, for instance, on my workout, well, the plates themselves probably only weighed about 40 or 50 pounds. But I was getting about an IMA of 3 the other direction. I guess technically an IMA of a third the direction that I was working it. So anyway, want to kind of share that with you. All right, so what we have here is an IMA of 5, and so what I did was I took basically the same setup I had last time, but this time notice the movable pulley is where the anchor point is at. And so we've got the same 4 strands going across around the pulleys, but now by doing it this way, I redirected the free strand to come up here. And so now with the free strand going upward, I'm able to get a 5th upward strand. Now, there's 6 strands, of course, total, as you see here. But the 6th strand is still down, it doesn't count. So this is your IMA of 5. Again, I've got 200 grams balancing 1,000 grams. And again, you notice there's a 5 times difference. I mean, look at how high this mass goes. Now look how far down it goes. And notice that the 1,000 gram mass moved that much for that to go considerably higher. So again, you're getting that distance, the difference of distance instead of force. So you trade the force for distance.